Right, this is the start of Unit 2 in the higher course. The first thing that we start looking at is differentiation, which is the first part of calculus that you'll see. It's important for a lot of factors, and it will come up kind of twice in the higher course. So we're going to basically focus on the basics just now, and then we're going to put it into a context when we get to, I think, not until Unit 3. Okay. But calculus in general is the part of mathematics which deals with understanding change. And more specifically for differentiation, it's the rate of change. And it allows us to model, describe, and predict many types of behavior and phenomena. So there's a couple of different examples of where we use it here. We're not necessarily going to be using these in terms of maths. There's kind of a third example, or a fourth, example of where we use this in maths. But out with maths, or out with what we're going to do in the classroom at least, we can find the instantaneous speed of a parachutist falling from a plane. Obviously, there's kind of similar context to that. It's not just to do with parachutists. How quickly an infection will spread after the outbreak of a disease. Given I wrote this about 3-4 years ago, that's very, very appropriate. And the future population of a country, okay, which is appropriate as well. Differentiation, therefore, is particularly important for long-term planning. Okay, so you can think of how that would be used across a number of jobs. Right, consider an aeroplane flying at a constant speed of 500 miles per hour. Right, this is going to be a basic kind of definition or description of how differentiation works. There's a process to it, which you'll probably find easier to understand once I go through some examples. Okay, it might almost be easier to come back through these slides at a later date once you've kind of got into a differentiation a bit more and see where it all ties in. Okay, but this is to explain actually what differentiation is. So this is going to be a graph showing the relationship between time and distance, which you've seen before. You do a lot in terms of speed, distance, time. And we've got this specific line, which is showing the aeroplane flying at a constant speed of 500 miles per hour. Okay, so the speed of the plane is the rate at which the distance being covered changes with respect to time. So that's this idea of rate of change. So in this case, the rate of change is 500 miles per hour. Okay, so from the graph showing us time against distance, we can work out speed. Okay, and speed is the first kind of example of rate of change that you'll deal with. Okay, so the speed of the plane can be calculated at any given point by finding the gradient of the line at that particular point. Okay, so this is the stuff you already know. I know you'd be thinking, what the hell is he on about? But this is stuff you already know. If we look at the gradient along any point of this line, and it's just a straight line, so it's the same gradient all the way along, then we can find the speed. Okay, so if we pick lots of different points, so you've got the point at the top here, 3006. Where's my mouse at? 3006, or 3000, sorry. You go 5, 2500, 4, 2000, so on and so forth. If we're trying to find the gradient at any one of those points, okay, then it's just the rise over run. And we can obviously use 0, 0. It basically just gives us the gradient as 500, okay? So the gradient is constant, the speed is constant, and thus the rate of change is constant, okay? But in a general sense, when we're talking about gradient and when we're talking about rate of change, they are the same thing. So gradient is the rate of change. Right, to find either of these things, okay, especially when we have a more awkward function, so we're going to differentiate from now on. So we're not generally going to be starting with the graph. So obviously we've used gradient in terms of graphs quite a lot in terms of points. But what we're going to be dealing with from now on is a function, so an actual equation of something, and we want to take that and we want to find the rate of change. And it's the same thing as finding the gradient. It's just a little bit more complicated when we've just got a function, okay? So bear with me. I'm not showing you how to do this yet, so don't panic just yet. But this is just getting us into what differentiation actually is. Okay, so in mathematics, the process of calculating rate of change is called differentiation. Okay? In this graph, the equation of line is given by y equals 500x. Okay, the distance y is a function of the time x. We could also write f of x equals 500x. These are all just kind of much the same thing. When we differentiate this function, we get the gradient of the line. So you don't know how to differentiate yet, so don't worry too much. But the idea is we're going to go from this, and we're going to differentiate it to the point where we just get the gradient, which we already know is 500. Okay, so it's not just a case of scoring out the x. It's not quite as simple as that. This gives us the rate of change of the function. The rate of change is known as the derivative of the function. So this is, as much as anything else, this is us getting used to the language used around differentiation. So we've got the derivative of the function. We differentiate a function. It's just getting used to the different, as I say, words used around this. Okay. So for the function that we've got here, y equals f of 500x, the following statements are equivalent. So the gradient of the graph of the function is 500. We already established that. The rate of change of y with respect to x. So you can see the two axes, y and x. So the rate of change of y, so this changes with respect to that, is 500. Okay, and the derivative of y with respect to x is 500. So it's all the same thing. These are all equivalent, but they're going to be kind of phrases that I use interchangeably from now on, and you'll hear used quite a lot in terms of a roundabout differentiation. Okay. Right, the way that we write, in other words, notation, is very important in terms of differentiation. So depending on the function that we are deriving, there are several ways in which we can write the same thing. So this is just a wee table just to show you what we mean. Okay, so this is the original function. Now, you've already dealt with this. You can have y equals 500x, and you can have f of x equals 500x. It's just the same thing. It's just a different way of writing it. But obviously, when we differentiate, we have to kind of follow through the original function. So when we write this differentiated, okay, so we already know that this differentiated is 500. You don't know how yet, but we know that the gradient is equivalent to the rate of change is equivalent to the derivative. Okay, so we know it's 500, but the way we write this is what we call dy by dx, and that's equal to 500. Okay, and then in this case, it's a little bit more straightforward. If we've got f of x as our original function, when it's differentiated, in other words, f dash x in this case, is equal to 500. So just two different ways of writing it, and it depends obviously what the question is in terms of where you start in terms of how we write the derivative. Okay. So if it's y equals, then the derivative will be dy by dx. If we start the function as f of x, then it'll be f dash x. Just be very, very careful here. Don't get this confused with the inverse function, okay? If you don't look closely enough, then you can often get the two confused, because obviously an inverse function might be f of minus 1x. So they look very, very similar, can easily be confused, so just be careful there, okay? Right, we will mainly be deriving functions of the form y equals x squared, y equals ax cubed, y equals sin x, all these different kind of things. So more basic functions, okay? We can look at this graphically too, however, it is easier to do so algebraically. So we could draw these out, and I'm going to draw this out just to kind of show you how it works. But what I'm going to show you eventually, and I've still not got to this yet, so don't panic just yet, I've still not actually showed you how to differentiate algebraically, okay? But this is it, okay? This is a simple rule. This is going to be, your life throughout higher in many ways. So if we have a function of this form, and obviously there's different ways of changing this, but if we have y equals x to the power of n, so we're going to be dealing with a lot with indices. So those of you that have been at home have been practicing that. So this is basically y. So y equals x to the power of n, okay? And then when we differentiate, in other words, the dy by dx of this function would be this kind of index multiplied by the function now, and then the index dropped by 1, okay? And I'm going to show you some examples of this in a minute, okay? And it will hopefully make a bit more sense. But that's your rule, so make sure you've got that copied down nice and clear, okay? Right, we often have a function made up of several parts. In other words, there's a plus or a minus in between them, okay? And it might look a bit more confusing, but what we actually do when we're differentiating is we differentiate each part separately, okay? So again, say a function y is made up of a function f of x and a function g of x. So just something along the lines of x squared plus x, for example, okay? Then the derivative will be each of those functions differentiated separately, okay? So we don't need to combine them in any way yet. They will just be differentiated separately, and we don't have to kind of think about how one reacts with the other, okay? If they were multiplied, it's a different story entirely, but you generally don't cover that until advanced higher, okay? Right, and just a couple of little notes at the bottom here. The derivative of a constant, so if we just had 1, 2, 3, 4, just a number basically, where there's no x attached. In other words, if y equals c, where c is a constant, then the derivative will equal 0. So the derivative of 1 is 0. The derivative of 7 halves is 0. The derivative of minus 0.3 is 0. If it's just a number, just a constant, then the derivative is 0. So then if you had something that was just x, or something multiplied by x, then the derivative just becomes that constant. That's actually following this rule, because technically if you've got cx, then the power is 1, and if you times by that, then nothing changes, and then you drop it by 1, it becomes 0, and anything to the power of 0 is just 1. So what happens in theory is that the x just disappears. You get some more examples of this in a minute. Right, this is a proof, okay, to show you how differentiation works in terms of a graph. So this is a graph of 5x squared, okay? Right, going by the rules of derivatives, the gradient, which is the same as the rate of change or the derivative, when x is 2. So we're looking for a specific point here, which is that point there, okay? So going by the rule, okay, so we've got our function, we're trying to find the derivative at a specific point, so we'd have to follow this. So what's basically going to happen, we've got something like this, 5x squared. So we're going to take the power, we're going to take the index, and we're going to multiply it by our function now. So if we multiply by 2, that just becomes 10x. Then when at the same time, simultaneously, we have to drop this by 1. Okay, so it just reduces by 1, in which case it just becomes 1, in which case the derivative is just 10x, okay? So at that specific point, we're not going to be doing too much of this just yet, but at that specific point, then the gradient is 20 because it just becomes 10 times by the point that it's at. In other words, 10 times by 2, which is 20. Okay. Right, if we look at a separate point entirely, so we're looking at x equal 4 now, which is that point there. Okay, we do the same thing. Okay, that's not right. I don't know where that 4's come from. I'll delete that in a second. But that's just the derivative is just the same. Okay, so it's 10x. So just ignore that 4. In which case it becomes 10 times by 4. Okay, when we substitute the 4 in, 10 times by 4, which is 40. Right. That's just showing you in terms of algebraically, but I want to look at this in terms of the graph. Okay. So we can look at rate of change in terms of the gradient of a tangent. Okay, in other words, the gradient of those two lines there. So we all know a tangent is just the point where it cuts it, a line that touches it at one point. So it would look like those two lines. And what we're basically going to prove is that by finding the gradient of these two lines, we'll find that the rate of change is exactly the same. Okay, so it gives us two options, but generally we're just going to stick with the algebraic one because we don't want to faff around drawing lines. Okay, so right. Oh, make that bigger. Yeah, that's just not quite clear, so I'll make that a little bit bigger. Right, so from the red line, if we just pick 2 points, I've got a point there which is roughly 1,5, and the other point is roughly 345. Okay, if we're trying to find the gradient of that line, okay, we've got 2 points, so we can use our gradient formula, and it gives us 20, which, as we already discovered, is exactly the same as the rate of change. Okay, do the same kind of thing with the green line. We've got 2 points, a point there and a point there, 3.5, 60, and 4.5, 100. If we find the gradient between those two lines, it's 40, which is the same as what we found before. Okay, so we can use either method to find the rate of change. So we can differentiate, but obviously there's less working required. So when we did this version at the start, when we just differentiated and subbed in the value, it was a little bit easier. We didn't have to find points. We didn't have to use the gradient formula. It was a little bit easier to do that. Okay. Right, so some quick examples for you. So 5 different examples here of different things in terms of differentiation. Okay. So we're using that formula. So in terms of this first one, if we've got it in the form x to the power of something, we're going to come to this later when it's not quite in this form, but just now, these are all in the form that we want them to be. Okay, so we take the power, we multiply by that power, and then we drop the power by 1. So the derivative is just 6x to the power of 5. Okay, because the function was y equals, then our derivative will be dy by dx equals. So times by 6, drop the power by 1, 6x to the power of 5, that's it. The second part before was finding the rate of change at a specific point. Okay, but once we found the derivative, we can find the rate of change at any point. So we're just cutting off at this point. If it said find the rate of change when x is 6, then I'd substitute the 6 into the derivative. But we're not worried about that just yet. So for the second one, same idea. We're going to multiply by the power and then drop it by 1. Just remember that 1 less than -4 is -5. So it's -4x to the power of -5. And generally when we're dealing with these, we want them in with a positive power, in which case we change this like we did with indices in that 5. X to the power of -5 is 1 over x to the power of 5. So this becomes -4 over x to the power of 5. So for the next one, okay, we multiply by the power and then drop it by 1. You just got to remember in terms of your fractions. If we drop this by 1, it's the same as dropping it by 2 over 2, which becomes 5 over 2. Okay, so it's 7 over 2 times by x to the power of 5 over 2. And you can rewrite that. Remember, power of 5 over 2 is just the square root of x to the power of 5. Okay, so for the next one, again, you times by a half, but you just times the 5 by a half this time and drop a half by 1, which becomes -1/2. So it becomes 5 over 2 times by x to the power of -1/2. And you can rewrite x to the power of -1/2 as basically 1 over root x. So we can rewrite it like that. The point is we're going to use this in a second. We're going to use this in a step further. So we want to write it in the simplest possible form. And the last one is basically just showing the idea that if you have lots of functions or parts of a function added together, you just differentiate each one individually. 12x to the power of 3. This becomes -4x to the power of 0. You drop it by 1, it just becomes x to the power of 0, and a constant just disappears. So it's just 12x cubed minus 4. Okay?